Hey everyone, we're going to be in Chapter 8 looking at substitution reactions of alkyl halides. So the word that's important in this chapter, we're looking at a new reaction type, substitution reactions. When we looked at alkenes and alkynes, we did addition reactions where we added atoms or groups of atoms across the pi bond. But in the substitution reaction, we are substituting an atom or group of atoms for another atom or group of atoms. So the specific type of substitution reactions we're going to be looking at are nucleophilic substitution reactions. These are substitution reactions where a nucleophile is going to react with a substituted hydrocarbon, and the nucleophile will replace that hydrocarbon. The nucleophile reacts with the hydrocarbon and replaces one of the atoms. So the LV here on the hydrocarbon represents a leaving group. This is the group that will leave the hydrocarbon. Leaving group in this chapter will be halides. The leaving groups here are going to be halides, like fluorine, chlorine, bromine, iodine. So what we'll be looking at is a reaction between a nucleophile then, and if we have a hydrocarbon with a halide attached, we have alkyl halides reacting with nucleophiles. Alright, so for these nucleophilic substitution reactions, there's two reactions we're going to look at in this chapter. The first type that we're going to discuss are Sn2 reactions, and the second type we're going to look at are Sn1 reactions. Now, these are the names of the reactions, and the S in the name stands for a substitution reaction. The N stands for of a nucleophile. The nucleophile will be substituting. And then the 1 and 2 represent the overall kinetics of the reaction. And the rate-determining step of both mechanisms is their kinetics unimolecular or is it bimolecular? All right. So let's start off by looking at Sn2 reactions. In Sn2 reactions, the simpler of the two mechanistically, because it only involves one step. If you look in the reaction here, what we have is a nucleophile. Remember, nucleophiles are negative. They have either a full negative charge or a pair of electrons that show partial negative charge on an atom. And it's going to attack the electrophilic carbon here, because in an alkyl halide, recall that the halide is partial negative and the carbon it's attached to is partial positive. So our reacting electrophilic atom will be this partial positive carbon that the nucleophile is attached to. So in the mechanism, the nucleophile approaches from behind the CX bond. If it's facing one direction, we've got tetrahedral sp3 hydrocarbon, carbon atom. The nucleophile comes in from the back and makes a bond with that tetrahedral carbon from a backside attack. Now carbon can only have 4 bonds, so as the nucleophile forms a bond, the halide breaks its bond. So we make a bond and break a bond in the same step. And we end up adding the nucleophile to the carbon chain, and the halide anion is the leaving group that goes away. So this is the one-step reaction. All right, it literally, all of the bond making and breaking occurs in one step. What I've shown here in the middle, of the reaction is the transition state. Now, a transition state is not an intermediate. If we look over here at the reaction diagram, there's the reactants, we've got our products, and all we have in between the reactants and products is the activation energy to make and break the bonds. And the amount of activation energy it takes to make and break the bonds is the amount of energy to get to partial bonds in the transition state. So this is not an intermediate, it's the highest energy part of the reaction. So what does the transition state look like here? The transition state shows the nucleophile partially bonded to carbon as it's starting to make a bond, and the bond is starting to break for the halide. So we have 2 partial bonds here, and there's a partial negative charge on either side. So we have a charged transition state. There's partial negative charges overall on either side of the hydrocarbon. The other thing to notice is the tetrahedral structure of the reactive electrophilic carbon is changing. If we look over here, the tetrahedral structure has the 3 other bonded atoms on the carbon pointing this way. In the transition state, because there's 5 things about the central carbon, 2 partial bonds and then 3 rel bonds, we see a planarization of those 3 other groups on carbon. And once the reaction's over and the nucleophile has added to the other side, we see now the tetrahedral, the other 3 atoms are facing the opposite direction as they were initially. We were facing this way, now we're facing this way. If we look at the stereochemistry, the 3-dimension of what's happened about the reacting carbon, we see that there is an inversion of stereochemistry. Now all of these things are important, and they are the mechanism explains these characteristics well, but we're going to discuss these characteristics individually. So the first characteristic explained by the mechanism that we're looking at is the kinetics. Remember I said this is a one-step mechanism. The reactants go to the product. So there's a nucleophile there, and their halide disperses. So the reactants go directly to products in a one-step mechanism. Because it's one step, if we look at the kinetics, the only step must be the rate-determining step of the reaction. The kinetics of the reaction are always determined by the slowest or the rate-limiting step. So if this is the only step, here we have a rate constant for this step. So the rate of the reaction equals the rate constant times the concentration of the reactants at that step. There are 2 reactants at that step, the alkyl halide, Rx, and the nucleophile. So there are 2 molecules involved in the rate-determining step. So what we say is that this reaction is bimolecular. So it's a substitution reaction where a nucleophile substitutes, and the reaction is bimolecular. Alright? Okay, so that's what the 2 stands for. Now, the other thing we talked about with the mechanism was the stereochemistry. In this mechanism, the backside attack of the nucleophile on the alkyl halide, we get an inversion of configuration about the reacting or electrophilic carbon. This becomes important if you create chiral carbons. If you start with a chiral carbon and you substitute to form another chiral carbon, you invert the configuration about that carbon due to the backside attack. The other thing that's important about this reaction that we'll be discussing in the chapter is the overall reactivity of the substrate Rx, which is this compound. Now, we talked about this in a previous chapter, but there are different classifications of alkyl halides. If an alkyl halide, a CX bond, has 3 hydrogens bonded to it, we call it a methyl alkyl halide. But if the alkyl halide has 2 hydrogens and 1 R group bonded to it, the carbon has 1 R group bonded to it and 2 hydrogens, we call that a primary alkyl halide. And if there are 2 carbon chains bonded to the electrophilic carbon, the carbon attached to the halogen, then we call it a secondary alkyl halide. And then finally, if there are 3 R groups attached to the atom attached to the halogen, we call it a tertiary alkyl halide. So these are the classifications we talked about previously of the alkyl halides. It turns out that the more substituted the electrophilic carbon is with R groups, the slower the Sn2 reaction will occur. This is because in order for the reaction to occur at a reasonable rate, the nucleophile has to attack from the back side, so there has to be space in the back for the bond to form without repulsion of other larger groups blocking the backside of the alkyl halide. So methyl groups, because they only have hydrogens, which are small, react the fastest. Methyl halides react the fastest. And then primary alkyl halides. Your primary alkyl halides and your methyls, alkyl halides, will always do Sn2 reactions. They'll always do Sn2 because they're unhindered and the nucleophile can come in the backside. Secondary alkyl halides are a little bit more bulky, so sometimes the reactions will proceed through this backside attack, single-step mechanism of an Sn2, but they can also, depending on other conditions, prefer an Sn1 mechanism. So we'll have to talk about other characteristics of the reaction to be able to determine whether or not the compound can do an Sn2 or not. Now, tertiary alkyl halides are so sterically hindered from the backside that, and there's so much bulk, that there's too much steric repulsion. Tertiaries never do Sn2 reactions. Tertiary alkyl halides are too bulky to do Sn2 reactions, and they will not. Okay, another thing that influences substitution reactions is the nucleophile that's attacking, or the reagent that's reacting with the alkyl halide. So here we have the nucleophile reacting, also known as the reagent. Now, what we need is a really good nucleophile to get an Sn2 reaction. In order for it to form a bond and break a bond, the nucleophile has to be really good. This has to do with things such as full negative charge, a small nucleophile so it can fit into the backside, polarizability so it can form that bond quickly, kinetically. So all of these things we'll talk about later, but we need a good nucleophile in order to get a good Sn2 reaction. The last thing we need to discuss is the solvent. Remember, this went through a charged transition state. So if the transition state is charged, remember the transition state's the highest point of energy in the reaction, going from reactants to products. In order to lower the activation energy and make the reaction feasible at a decent rate, we need to stabilize the transition state, which is charged, by using a solvent that stabilizes it or interacts with it. So we need a charged solvent as well. We're not talking ionic solvent, we're talking about polar solvents. So we need a polar solvent. Now, there are several types of polar compounds. Anytime you have an electronegative atom attached to carbon, you get a polar organic solvent. But we don't only need it to be polar, we need it to be aprotic or non-acidic. We don't want hydrogens attached to oxygens as solvents, because those are protic, and what we're going to find later on is those will tend to prefer an Sn1 type mechanism, not an Sn2 reaction. So we want a polar aprotic solvent. Good examples of polar aprotic solvents are acetone, which is a carbonyl, a ketone with two methyl groups on either side. DMSO, dimethyl sulfoxide, two methyl groups with a sulfur-oxygen double bond in the middle. So the sulfur analog of acetone, dimethyl sulfoxide, DMSO. And then also, we have the carbonyl here, once again very polar, but this is an amide functionality because it's a nitrogen bonded to carbonyl. But notice on the nitrogen, no hydrogens attached. We've got two methyl groups instead. So it's a dimethyl formamide is the name of this compound, also known as DMF. For now, I'd just like you to know that we need these polar aprotic solvents. Acetone, DMSO, and DMF are typically popular ones. But there are others as well. So let's look at an example of an Sn2 reaction. Here we have a nucleophile. This compound has a negative charge on the oxygen, so that's our nucleophile. The sodium is just acting as a counterion. It actually doesn't do anything in the reaction. Now we know that the nucleophiles react with the alkyl halides. So our alkyl halide here is ethyl bromide. And from the ethyl bromide, the bromide is our leaving group. So when the reaction occurs, remember the nucleophile will make the bond, the halide bond will break, and we'll end up getting the nucleophile attached to the reactive electrophilic carbon. So what will that look like in this reaction? Well, let's look at the mechanism. Remember, oxygen's got its lone pairs. So the negative charge will attack the electrophilic carbon, the carbon attached to the halide, will make a bond, and we break a bond, the alkyl halide bond, all in one step, and we immediately form the product. Now in the product, we've got, for the alkyl halide, we've got CH3, CH2, still as our hydrocarbon chain, but instead of bromine, now we have the oxygen, which has been bonded, and it also has a CH2, CH3 bonded. So we've made this compound, also known as diethyl ether. The side product of the reaction, because bromide goes away, and sodium as a counterion, is the sodium bromide salt. But this is the organic product of the reaction. So that's a simple Sn2. What we're going to do in the rest of the chapter is we are going to look at some more examples and then the scopes of the reactions and things. Alright, so here we have another reaction up at the top, and it is chlorocyclohexane plus potassium cyanide. We haven't really talked much about cyanide yet. So cyanide is a nucleophile. There we go. Where carbon, where carbon has, keep going back, a negative charge. There we go. Carbon has a negative charge on it. Let me try to redraw that. Here. So the carbon of cyanide is negative. So that is our nucleophilic atom right there. And the carbon, with its pair of electrons, will bond to the electrophilic carbon of the alkyl halide. So let's draw our cyanide. And we're reacting with the alkyl chloride. We'll make a bond at the electrophilic carbon, and we'll break the halogen bond. So our product now, the alkyl part of the alkyl halide is left, but instead of chlorine, we've put a cyanide in its place. So this is a cyano compound now of cyclohexane. Alright, let's look at the next one. The next one we have a benzyl bromide, a bromine attached to the benzyl carbon here. And we've got trimethylamine. So this is our nucleophile, the nitrogen, because it's got the negative charge. It's going to react at the benzylic carbon, and we're going to make a bond. We break a bond. The halide removes. So we substitute the halogen with the trimethylamine. So when we draw this product, the alkyl part of the alkyl halide, once again, that benzene doesn't change. We've got a CH2, and now the bromide's not attached. The nitrogen with its 3 methyl groups is attached. Now, nitrogen's got 4 bonds here. It gave up its electrons to form that bond. So now we have an ammonium cation. The anion, the byproduct of this reaction, is the bromide. So here we have an ammonium salt. We have a trimethyl amine with a benzyl group on it, and then we've got the bromide anion. Alright, let's look at the last one here. Notice in the last example, our alkyl halide shows stereochemistry. There's a wedge right there. So that's a chiral carbon. It actually is. So remember, when we do an Sn2 reaction, we get an inversion of stereochemistry. So once again, we're seeing the cyanide is our nucleophile, and it's going to do a backside attack. So it comes in from the back, and it pushes out the bromide. So we can get an inversion of stereochemistry at that carbon. Now the methyl group on the top did not react, so its stereochemistry stays up. But now instead of the bromide up, we get the cyano group down. So do you see how the up went to down at that carbon? That is the inversion of stereochemistry in an Sn2 reaction. Alright, just cleaning things up here. Okay, so what's the scope of the reaction? Well, we have in this chapter for Sn2 reactions, all of our reactive substrates are the electrophilic atoms are going to be alkyl halides, so that's all the same. But the versatility and the power in this reaction comes from the fact that we, as you see in these examples that we're starting with, have several different nucleophiles that we can use. Here we have an iodide, a hydroxide, an alkoxide. We have some sulfur compounds. We have amines. We have azides. We have there's one we discussed in chapter 6, the triple bond carbon. Oops. Where'd it go? Okay, there we go. I fixed it. So here we see the acetylide anion that we've seen before, where we have the triple bond carbon. So this is a substituted acetylide. The anion, that was from our alkyne chapter when we deprotonate with something like sodium amide or sodium hydride, a terminal alkyne. But we can create this nucleophile that will react and do a substitution reaction. So just another nucleophile. We have the cyano group, the cyanide. Okay. And we have carboxylate anions, the deprotonated carboxylic acids. We have phosphines. So we have several different nucleophiles where we have some type of atom that contains a negative charge or just it's neutral. Notice the neutral ones are really polarizable or good bases also, like the amines, the sulfurs. But most of the time they're negative anions as nucleophiles. And so because we have a large versatility of nucleophiles to use this reaction with any alkyl halide we choose, we can form several different functional groups in a simple Sn2 reaction. We can form alkyl halides, we can form alcohols, ethers, thiols, which are the sulfur version of alcohols, thioethers, which are the sulfur version of ethers. We can form amines, and here this is an ammonium ion. If you treat it with base, you can deprotonate and get back to the amine. Azides, alkynes, substituted alkynes, nitriles. Whenever you put a carbon triple bond nitrogen on a ring, that functional group is called a nitrile. We can form esters, which are carbonyls with an OR group attached to them. That's a new functional group, an ester. We'll discuss that more in organic too. And we just have a lot of versatility with the types of molecules that we can make. So Sn2 reactions are very popular because they're so powerful.